In section 2.2, we're going to be taking a look at the limit of a function. All of chapter 2 is about limits, and we will be using limits throughout the entire semester. So it's a very, very important concept. We briefly alluded to it in the last section. We're going to start to really focus on it now. So if I write the limit as x approaches a of f of x equals L. So this is the notation that we'll use. We write lim, L-I-M. There's a subscript where we say x is approaching a. So a would be a particular x value that we're getting close to. And then we name the function, and we say that's equal to L. And what this means is that as x gets close to a, f of x gets close to L. Here I'm using this arrow notation, which you saw a little bit of in pre-calculus, to say that these things are getting close. Notice f of x is just a fancy name for my y value. So L, this thing that we're calling the limit, is the y value that we're getting close to. Now I could write this out in words. As x gets arbitrarily close to a, and there's an important caveat here. Okay. Arbitrarily close to a without necessarily equaling a. Okay. So if I were actually at an x value of a, the distance between where I am and a would be 0. That's as close as you can possibly get. We're not considering that. We're considering that we're close to but not at a. Okay. Then f of x gets arbitrarily close to this number L. So as our x values get close to this number a, our y values get close to this number L. And you'll notice there's no caveat here that f of x can't equal L. It's okay if we have equality in the y values, but we're not going to consider what happens at a. Okay. Now, I like to phrase it this way, because it's because x gets close to a that f of x is going to get close to L. I will just mention that your book gives you this same informal definition of limit, but it just reverses the order. It says f of x gets close to L when x gets close to a. It means exactly the same thing, it's just the flexibility of the English language. All right. Now, what does this actually mean? Well, I'm going to draw a couple pictures of some examples. So here's a function, f of x, and there's a hole in the graph right here. And I can see the x value of the hole is a, and the y value of the hole is L. This would be an example where as x gets close to a, f of x gets close to L. If I follow the graph in, coming from either side, I'm kind of expecting there to be a point there. And the reason I'm expecting there to be a point there is because we're getting closer and closer and closer to that point. So the limit as x approaches a of f of x would equal L in this case. The limit is telling me what do I expect to get? What's the y value that I expect based on the nearby behavior? Okay. Now, it would be entirely possible for me to have a function that looked something like this, where here there's actually a point instead of a hole on the graph of f. So now there's a point at A, and the y value there is L. Well, as I get closer and closer to A, coming in from either direction, I'm expecting there to be a point there. The only difference is that here, what I expect actually happens, and here, what I expect doesn't happen. We would still say here that as x gets close to A, f of x gets close to L, or the limit as x approaches A of f of x is L. Okay. So it's okay. You don't have to have a hole in the graph to use limits. But the reason limits are useful is for situations like this. This situation is a situation where I expect there to be a point there, and there is. So if I were to ask, what do I get and what do I expect, the answer to those two questions would be the same. If that was always the case, it would be kind of silly to have two different questions we could ask. We'd just say, what do we get? And we'd know we always get what we expect. But we have situations like this, where we expect something, but it's not what we get. It's a very important moment to point out that calculus can be a metaphor for life. In life, sometimes you expect things, and you don't get what you expect. Other times, you do. It's amazing, and calculus illustrates that for us beautifully. I'll just point out, I could put a point up here. So now the y value of this point would be f of A. That would be what I get when I plug A into f. It doesn't change the fact that the limit as x approaches A of f of x is L. The limit is the y value that I expect to get based on the nearby behavior, regardless of whether I get anything at all or whether I get what I expect. So the limit would be the y value of the hole. The function value would be the y value of the point. And it's possible to have any combination of things where they could agree, they could both exist but be different. A moment ago, the function value didn't exist, but the limit did exist. So limits are particularly useful at places where a function is not defined. And those are going to be the interesting limits that we take a look at. But it's not part of the definition that the function can't be defined at that point. It certainly could be. All right. So we saw an example that looked something like this. And this is going to be one of the applications that we're going to use for our limits. In the last section, we were taking a look at graphs of functions. For example, we had x squared, and we were looking at the point 1, 1, and we were creating these secant lines that passed through that point and another point. And we said we were using those because we wanted the x value of our point to get really, 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 really close to the x value 1, which was our point of tangency. We were hoping that we would notice a pattern so that the slopes of those secant lines would approach the slope of the tangent line. And if you remember, we actually calculated a function that we called m of x that was giving us the slope of the secant line. And when we did this for x squared at the point 1, 1, we actually got a graph that looked something like this. It was x plus 1, but with the restriction that x wasn't allowed to be 1. So that put a hole in the graph. But that hole had a really significant meaning, because that told us that as the x value of this second point got really, really close to the x value of our first point, the slopes of the secant lines got really, really close to, it turned out, 2. And that number, that y value of the hole, was the slope of the tangent line. Okay, so we're going to spend chapter 2 developing a bunch of techniques for evaluating limits. We're going to become masters of taking the limit of a function. And once we've done that, we're going to return to this problem of the derivative or the slope of the secant line, or sorry, the slope of the tangent line, and apply what we've learned about limits to finding the slope of the tangent line or the derivative. That's going to be chapter 3. Okay, that's where we're going.